When certain ionic compounds are formed, so for example, copper sulfate, water molecules can become trapped within the crystal. When this happens, we form something called a hydrate or a hydrated formula unit or compound. These water molecules are trapped within the crystal and they are attached to the formula unit according to a very specific ratio. This water is called water of crystallization, and you do need to know how to work with this when it comes to chemistry and stoichiometry calculations. Here are some examples of some hydrated crystals. They're called hydrates. We can say that they are hydrated, meaning they contain water. They are hydrous compounds. They contain a water of crystallization. And as you can see, when we represent the formula, the molecular formula, the number of moles of water, the number of water molecules is represented over here after the dots. So for example, copper sulfate, here we have 5 molecules of water within this formula unit, trapped within this compound. So essentially we've got a 1:5 ratio over here. Now we can ask you questions such as calculate the percentage of water by mass in a hydrated compound. We can also ask you the following. Calculate the number of moles of water of crystallization. And as you can see over here on the screen, we can represent this by an X, we can represent this by an N. Essentially, you have to find out the number of moles over here. And we can do this in the following way. Practically or experimentally, we can weigh, say for example, a certain mass, 100 grams of a hydrated crystal. We can put that in a test tube. Then we heat the test tube. And in this diagram over here, they are heating the test tube. They are heating the hydrated compound over a Bunsen burner. This is my heat source. So over here, they say copper sulfate crystals. This will essentially remove the water. The water will be evaporated. So we heat it over a period of time until all the water is removed. We will know that this is the case when the mass no longer decreases and water droplets are no longer forming on the side of the test tube. You see over here, they indicate that water droplets form. This is when the evaporation of the water is taking place. We are then able to weigh the crystals again. Now remember, now they no longer contain the water molecules trapped inside. And that is how we can determine the number of moles of H2O that was removed. So in this video, we're going to be doing exactly that. We're going to be looking at how to calculate the number of moles of water of crystallization, as well as the percentage of water crystallization by mass. Let's first look at how to calculate the percentage of water, and this is by mass, in CuCl2.2H2O. Now this 2 means that I have 2 water molecules trapped within this formula unit, so it's a 1:2 ratio. Now how we do this, how to calculate the percentage of water, is basically how we calculate percentage composition. So to calculate the percentage of water, the percentage of H2O, what we're essentially going to do is we're going to look at the mass of H2O within this particular compound or formula unit, divided by the total mass of the compound. And when I say the total mass of the compound or the formula unit, I mean the entire thing, including the water. And because we're looking for a percentage, we're multiplying it by 100. Now this is percentage by mass, and essentially we're looking at the molar mass. We need our periodic table to help us with this. Now, the first thing that I'm going to do is I'm going to look for the total mass. I always do percentage composition by looking for the total mass of the compound first. Now, when I say total mass, I'm looking at CuCl2.2H2O. When looking for this mass, what we're going to do is we're going to take the atomic mass of copper. You look at your periodic table in order to find this. The atomic mass numbers are the big numbers. So for copper, it's 63,5. And if you look at your compound, you only have 1 copper atom in this compound. So it's just 63,5. And then we're going to add the atomic mass number of chlorine. However, we have 2 chlorine atoms in this compound. So we look at chlorine, we still see chlorine is 35,5. So we're going to say 35,5 times 2. Why times 2? Because there's 2 chlorine atoms. Then we do the same thing for the hydrogens and the oxygens. The very important thing, and where people often go wrong in this question, is they think that the dot means multiply. It does not mean multiply. In maths, a dot or a point does represent multiply, but in this context, it doesn't. So we just need to continue adding the atomic mass numbers for each element like normal. So hydrogen over here, we've got 2 times 2. This 2 over here represents 2 water molecules. So it covers both the hydrogen and the oxygen. So 2 times 2, we have 4 hydrogens and we have 2 oxygens. Now the atomic mass for hydrogen is 1. And as I said, we have 4 hydrogens. Then we add the atomic mass number for oxygen is 16. We have 2 oxygens because the big 2 applies to the oxygen as well. Then we just add up all of that together and we get the total mass. And remember, that's the denominator of the fraction. So let's do that. We're going to get our denominator over there. We get 170,5 grams per mole. 170,5. So at the bottom, the total mass is 170,5. Now at the top is the mass of the water. Just the mass of the water. When I say the water, I mean the water within this compound. So it's this piece. And we kind of already worked that out. It's part of our first calculation. Remember, we had 4 hydrogens and the 2 oxygens. So it's this part over here. That is basically my numerator over there. Let's work that out quickly. That is 36 grams per mole. 36, and we multiply this entire thing by 100 because remember we're looking for the percentage of water. And my answer is 21.11%. So 21.11% of this compound is water. When the water molecules are obviously attached, when I heat it and remove the water, then obviously it's no longer there, then it's 0%. Let's look at how we calculate the number of moles of water of crystallization. So finding X or finding N in something like this. In this question, they say that we have 100 grams of hydrated AlCl3 crystals. So hydrated means that it contains molecules of water. Okay, cool. So we know there's water within the crystal. The crystal was heated until no further change in mass was observed. Now remember, when we heat the hydrated or hydrous compound, that causes the water to evaporate, therefore no more water molecules present in the formula unit anymore, just leaving AlCl3. They say the mass of the anhydrous crystal, in other words, the one that has no more water, is 55,28 grams. Calculate the number of moles of water of crystallization. They can call this N, they can call this X. Another way that they can represent this question is they can say, for example, they can give you AlCl3. They can put a N or a X over here. NH2O. They can give you the above information and they can say calculate N or calculate X. And that's the number of moles of water of crystallization. Now, how do you approach a question like this? Let's take a look. Now, remember, in order to find the number of moles of water of crystallization, what we're essentially doing is finding the ratio between this AlCl3 and the number of water molecules. So we're basically trying to find this part of the ratio, and that represents the number of moles of water of crystallization. So if I can work out the moles of the anhydrous compound, the number of moles of the anhydrous compound, and the number of moles of H2O, and I simplify that ratio, I can then work out the number of moles of water of crystallization. But how do I do that? My first step is to calculate the mass of the water that was lost. Now remember, we started off with 100. We ended with 55,28. This represented the hydrated crystal. In other words, the stuff with water. 55,28 represented the anhydrous compound. In other words, the stuff without water. So if 100 contains water and 55,28 does not contain water, the difference between these two numbers must be the mass of the water. So if I say 100 minus 55,28, I'm going to get the mass of the water that was lost or evaporated. So I've got 44,72 grams of H2O. Now, how does that help me? I now have the mass in grams of H2O 44,72 grams. I also have the mass in grams of the anhydrous crystal, basically just the AlCl3. So just this left part over here of my formula. That is 55,28 grams. Now remember, in stoichiometry, moles is absolutely everything. I'm looking for the number of moles of water of crystallization. So if I convert this to moles, and if I convert this to moles, I can put these two in a ratio. And if I simplify that ratio, remember what we're trying to do is we're trying to get the ratio between our anhydrous crystal over here and our water. What this basically is, it's a 1 to something ratio. It's a 1 to X or a 1 to N ratio. So if I can simplify this moles to this moles in a ratio, simplify that ratio to get 1 to something, then I've got my answer. So first step, work out the mass of the water that was evaporated, 44,72 grams. Convert both of them to moles, which we know how to do. We're going to use this formula. N is equal to mass divided by molar mass. Let's do that for AlCl3, and let's do that for H2O. So I write my formula once. Remember, I'm using this formula because I have the mass of the water that was lost or evaporated and the mass of the anhydrous crystal. I divide it by the molar mass, which I've done on the side here. I got these values from the periodic table, and then I work out the number of moles. Remember, we're not going to round off yet. There I've worked out the moles of my anhydrous crystal. So in other words, using the 55,28 grams because that does not contain the water. Therefore, I divided it by the molar mass of just AlCl3. Got the moles of that, worked out the moles of just the water, got that mass, remember, earlier, and I got 0,41408 and then 2,484444. Okay, the 4 is recurring. Remember, I want to work out N. It's a ratio between the anhydrous part of the crystal and my number of moles of water. At the moment, the ratio is like this. It's a 1 to N ratio. I need to work out what N is. So how do I get this ratio? So far I've got 0,414 and so on to 2,484 recurring. How do I get that ratio to be 1 to something? How do I get this number over here to become 1? Well, I divide this left part of the ratio, the 0,414, I divide that by itself, 0,41408. If I divide 0,41408 by itself, I get 1. What I do to the left-hand side of the ratio, I have to do to the other side of the ratio as well. If I divide the 2,484 by that same number, I get 5,999. And 5,999 is basically 6. I can round that up to 6. And we need it to be in a 1 to something ratio because as you can see over here, the big number in front of this is 1. 1 to N, we figured out that N, the right side of this ratio over here, is 6. Therefore, my number of moles of water of crystallization is 6 moles. Here's a past paper version of this question. Pause it, see if you can do it, and then do it with me. Mark your work with me. So they say we've got 14,2 grams of hydrated sodium carbonate. Remember, hydrated means that this 14,2 grams includes the water. It heats it until there's no further changes in mass. On heating, the water evaporates. They give me the little formula over here or the little equation, and they want the number of moles of water of crystallization, so they want N. In this case, they're calling it X. Doesn't matter. We want X, the number of moles of water of crystallization. In the sodium carbonate sample, if 5,3 grams of solid remained after the heating. Now remember, the solid that remains is the sodium carbonate, Na2CO3. So what we need to do first is we need to work out the mass of the water that was lost. So we take the hydrated mass, so that's the mass that contains the water. So this contains the sodium carbonate and the water. It represents this part of the equation. That's 14,2 grams. And we minus what was left over after the water evaporated, 5,3 grams. That corresponds to this part over here. That's 5,3 grams. The difference between those two numbers will give me the mass of the water. That is 8,9 grams of H2O. So I'm just going to write here 8,9 grams of H2O. 8,9 grams. But I need to work out the number of moles. I need to work out X. Now, after we've worked out the mass of water, what we're going to do is, remember, we want to work out this in our ratio. So if we take a look at Na2CO3 X H2O, this can essentially, the moles of both can be represented as a ratio, and the ratio, or the part of the ratio over here, is 1. So far we've got 1 to X. So if I work out the number of moles of sodium carbonate, just the sodium carbonate without the water, using this mass over here, the 5,3, and I work out the mass of just the water using this 8,9 over here, I convert them to moles. I simplify that ratio so that it is 1 to something. I can work out X. So let's convert to moles. To do this, I'm going to use this formula. My mass over here is 5,3 divided by my molar mass of sodium carbonate. You get this by using the periodic table, the atomic mass numbers. And I get 106 grams per mole using my periodic table to work out the number of moles for 5,3 divided by 106, and that is 0,05 moles, and that is of just the sodium carbonate. There's that. We do the same for water. Remember, the mass over here is 8,9 grams. The molar mass of water, it's 1 times 2, because that's of the hydrogen, plus 16. That is 18. We get number of moles of water as being 0,49444. That 4 is recurring moles of water. Now remember, we write that in a ratio, 0,05 to 0,494 recurring, and we want to simplify that ratio so that it is 1 to X. The 1 must be on the left hand side, because if we look at our hydrated formula, a hydrated compounds formula over here, we've got Na2CO3.XH2O. This Na2CO3, the number of moles of Na2CO3 is 1. So we need a 1 on the left-hand side of our ratio, and we're looking for X. So how do I simplify my ratio so that I have 1 on the left-hand side? I need a 1 over here. In order to get that to 1, I need to divide this by 0,05. What I do to the left-hand side, I do to the right-hand side, divide by 0,05. And you get 9,89, which is essentially 10. Don't forget to check the links in the description for more stoichiometry videos, more chemistry, more physics, more maths. I can't wait to see you in another video.